This is a famous pyramid, okay, diagram. At the bottom, we have components such as sensors, processors, communication modules. And at this level, we are focused on high fidelity design and performance analysis. It's really common to have different teams work in different components, right, based on their expertise. And these components are integrated into a single system, such as aircraft, vehicles. We then evaluate how the complete platforms perform its intended functions. And when we see these multiple systems are connected to form a system of system, we need to check the communications. We need to coordinate how they become critical, right? And at the top, we have a mission level. We are focused and shift from the system performance to mission outcome and operational effectiveness. Okay, I believe you are aware about this pyramid. It's very famous. And now we have all this animation. This is interesting because the key idea is that every engineering decision should ultimately trace back to the mission success. Instead of designing components first and hoping, they satisfy the mission, we start with this mission and systematically flow requirements down through the system. This pyramid is organized by different levels, as we saw, the mission level where we define operation objective, the system of system level where we multiply, the platforms and assets work together, the system level where we design individual system, and the component, it is going to the top to the down in high fidelity, where we detail this implementation. This is part of the mission engineering process, and we need to make sure if all these steps are working together, it's working perfectly. Now let's look into the key mission engineering challenges. Fernanda, you explained about this and this pyramid, mission engineering pyramid, but let's take a look at these challenges based on the industry. One of the biggest challenge in mission engineering is moving from individual system models to a mission level analysis. And we need to be able to model mission elements with the right level of detail, whether they are, sensors, platform, communication systems, or autonomous assets. The next challenge is integrate these elements into a coherent, system of systems, where we need to model and reuse. So this is a big challenge. Fernanda, I spent a lot of time of my engineering team, and we need to reuse this and then the next component, the next product that we are developing. This is a challenge, You need to develop at the same time, look to the future, right? And finally, the mission environments are constantly evolving. So what does it mean? So simulation must be scalable, adaptable, easy to refine as the requirements change. So usually MathWorks and all these tools for model-based address these challenges through the model-based approach. Okay, to enable engineers in different domains to develop, to integrate, and optimize these mission scenarios within, a unified environment. I don't want you as a manager, as of engineer, big engineering team, to spend a lot of time to understand different software components, software systems, and then you cannot reuse your system. The idea is totally the opposite, okay? The idea is to understand, to get familiar with these tools, and then to reuse, okay? At least part of these models. So you save money, okay? Engineering hours as well. A good example, as I mentioned, is a search and rescue mission from mission engineering system perspective. And this mission objective is to protect, to locate, and recover down personnel, right? And if you look into this example, the success depends on multiple systems working together, including, command center, C2 aircraft, satellite, rescue helicopters, communication networks, how to make sure is everything working, perfectly. Each system contributes a capability, but the mission success comes from their integration. We need to make sure if this integration is working. And the mission is divided into, I would say, in 4 phases, as we can see here. Search, ingress, execution, egress, truth, these tools that we are using, of course, MATLAB and Simulink. And we can module the systems, simulate the interaction and what is the impact of this, and evaluate the mission performance before deployment. Okay, these kind of testing of performance before deployment allows engineers to analyze the trade-off, identify possible issues, optimize the overall mission outcome rather than focus on individual platforms, because sometimes it can be working perfectly in one system, but if you integrate, it's a mess. So the essence of this mission engineering system of system approach. Okay, this is a very good example. So now, mission engineering delivers value to different stakeholders. I believe it's clear for everybody, right? From the government perspective, it helps decision makers understand the cause and effect relationships, identify capability gaps, evaluate alternatives, and explore the future opportunities before making the major investment. They are looking for the money and all this investment. For the contractors, the mission engineering provide a way to assess design options, optimize solutions, refine requirements, and demonstrate the mission level value early in the development process. We know all these companies is working to to make this easy in the best way, to follow all this model-based approach. And the common, I would say the common goal is improve the mission outcome by creating a mission level digital environment, a digital simulation to represent this mission. Organization can evaluate how the system work together, quantify operational effectiveness, and make better decision to, of course, reduce risk, right? And this is where these tools, model-based, enables collaboration between the government and the industry by providing a common framework for modeling, simulation, analysis, and emission level validation. Okay. I like this picture. When you define the mission through the descriptive models, and this diagram illustrates exactly the mission decomposition process. We'll begin with the mission objective, define the operation scenario, break it in representative vignettes, okay, to develop these mission threads that describe the operation activity. So we are partitioning, we are break our scenario to make sure if these activities, these operational activities working. And then we create a mission engineering threads that we can connect those activities to support in the systems and different technologies. I would say together these models define what, when, where, who, and how of this mission enable effective simulation and analysis. Let's go to the part 3, how we can represent a mission as a system of systems. I believe everybody knows, our audience, our attendees, most of you are MATLAB and Simulink users. To represent the mission as a system of systems requires more than, listening assets. We need to define this hierarchy of the mission and establish this interface between systems, assign the key attributes to components, and they capture the operational environment. These, I would say, this environment you can structure architecture that serves as a foundation for analysis and trade studies and for the mission evaluation. This is a correct tool to start analyze your mission, to start working your mission. Okay. And the mission engineer requires models, right, from many domains to work together. And MATLAB and Simulink provide a common environment where the system models, platforms models, communication networks, what else? Sensors, and the mission scenario can be integrated and evaluated as a complete system of systems. These tools enables engineers to assess mission effectiveness rather than focus on individual system or an isolation, a specific component. I would say the key takeaway in the mission engineer, it's not about modeling a platform, it's about understand how multiple systems work together to accomplish a mission. And I have another quick question. Please answer by chat. What is the field are you working in now? Satellite, maritime systems, radar systems, flight control, UAVs, our famous UAVs. Everybody's developing UAVs. Please share with me by chat. What is the field, the area are you working in? It's more satellite or aerospace industry, or more defense, focus on maritime, radar, flight control, UAVs. Share with us. We are curious to know. Oh, let's look into the mission problem statement and metrics. I want to start to provide you a workflow with these short videos and how we can do with MATLAB and Simulink and model-based approach, okay? So mission engineering starts with a mission question. In this example, what is the benefit of adding autonomous UAVs to a search and rescue mission? To answer this question, we need to measurable metrics, right? So it's not a quick answer. So we begin with the mission objective, recovering a personnel, or translate into a measure and effectiveness, such as time to allocate, secure, extract the personnel, as well as communication availability. So these measures are they linked to the low-level performance metrics, such as, I don't know, image capture capability, localization accuracy, communication throughout all this data transfer performance. I would say by establishing this traceability, we can evaluate how changes in the system design affect the mission outcomes and support informed decisions on investment, okay, requirements, and technology upgrades. So we are looking for these measures in terms of performance. We need to understand and to be measurable. Otherwise, we cannot answer all these questions, right? Let's start with the process and prepare the mission scenarios. The next step in the mission engineering workflow that I'm trying to show you is preparing the mission environment. In this example, we are using MATLAB, is using automatically to label and classify the mission region from geospatial imagery. So this workflow identifies different terrains and types of create a segmented map. Okay, let me run again. And in this case, engineers can then load in the segmented image, extract the valid mission area, review the generate classifications, and manually refine the terrain categories where if needed. So this process literally transforms raw geospatial data into a mission, ready environment, providing a realistic representation of operational area. And by this is preparation work, literally helps teams to check the mission scenarios faster because we are representing this map with a greater consistency, enable more accuracy and mission level analysis and simulation. Okay. If you want, I can share these details if you are interested in this. Now, once the mission scenario has been defined, the next step is establishing the preliminary system of system architecture. So we are using the requirements editor for traceability diagram in MATLAB. And we start defining the mission goal in this case. Okay, we can check the recovery personnel on the ground. You can see details. And from that mission, the objective, we identify the key user case and the functions required to achieve this success, such as target identification, path calculation, asset guidance, and the road optimization. So we can then establish traceability between the mission objective and these operational functions, literally ensuring that every activity directly contributes to the mission outcome. Have you used this tool before? Are you aware? At the same time, we define the mission assets and the actors involved in this case, in this example, and we can see exactly the main, this is aircraft we can see in the end. Okay, yeah, we can see the main aircraft, the land vehicle, the ground vehicle, and the multiple UAVs that you want to add in this mission. So the traceability basically is approach, to help all the engineers is working to understand how the mission goals, operational function, and the physical assets are connected. I have a quick question in this slide. Please answer by chat. How do you perform the impact analysis when the requirements change and ensure the traceability coverage? Will you be able to answer this question? Do you perform this kind of analysis? It happens, right? Something, you want to change the requirements, you want to see the impact. How can you make sure the traceability coverage? Please answer this question by chat. If you don't have, there is no problem. Fernanda, I don't perform this kind of analysis, but I'm interested. We can help as well. Now, let's take a look in architecture trade-offs. This is very important. The trade-off analysis is a fundamental part of the mission engineering because of the mission success, right? Depends on the balance of the multiple and competing factors. To improve one capability often impacts with another. So for example, increase the sensor coverage may require more power. Adding more assets may improve mission performance, but increase the cost and the complexity. And the high autonomy may reduce workload while introducing new operational considerations. So we need to be aware about this. And the objective is not to optimize a single system parameter, right? But to understand how different decisions affect overall the mission outcome. By evaluating alternatives early, we can identify the most effective architecture to reduce the risk and make informed decision based on the mission impact rather than assumption. So I believe this has happened, so this is not good, of course. And then the mission engineering helps answer a key question. Which combination of capabilities deliver the greatest mission value? So this is the reason we need to think about these trade-offs, okay? Analyze architecture performance. After evaluating different architecture options, the next step is to analyze their performance in realistic mission scenarios. The purpose is to understand whether the select architecture can actually achieve the mission objectives under, the operational condition. At this stage, we measure key mission metrics such as coverage, response time, communication availability, asset utilization, and overall the mission success. And you look into the performance analysis, what is the benefit to have this? It allows us to identify in all these details and validate the assumption, that we are thinking, and quantify the impact of the architecture decisions. So in this case, we are using the MATLAB app to provide all these scenarios, to check the lossy communication message, all this surveillance, details. So you can check not only the performance of this communication, but see the impact. Rather than asking which architecture looks the best on the paper, we are asking which architecture performs best in a mission environment. Okay, and literally this provides objective, I would say, evidence to support design decision and ensure that the chosen, system of systems architecture delivers the desired mission outcomes. We are always looking to outcome. Check the performance. We spoke about the trade-offs, and let's take a look in this example in system architecture. Here we model the key mission elements, including the ground vehicle drone, the target, the visualization environment, along with this interface that should be connected. In this case, we are using app as well to optimize this analysis, and each system can be decomposed into internal subsystems. For example, we have a drone, we can analyze the propulsion navigation, GPS, power systems details, and other, onboarding functions. In this level of details, we can perform system level trade-offs studies, okay, and understand how these components decision influence the overall the system performance. So we can evaluate in this example for battery behavior, discharge curves, assess the endurance and the limitation, and determine how power consumption impacts an emission duration. The goal here is to connect this detailed engineering decision and back to the system performance and ensure that each system can successfully support it in the broadened mission objective. So you can see in the same environment, we are checking the hierarchy based on the system, architecture. And then we are checking the battery, in this case, the power systems analysis, to understand what time this battery will be able to support my system based on the mission. Okay. Now let's take a look and simulate the component, including the logical and the physical part. In this example, we are focused on the drone and to check the internal design. And this include the flight control system, the navigation functions, the operational logic that, check its behavior. And the behavior aspects are represented through the state-based logic. We are using Stateflow, that allowing us to model and how the drone reacts to different mission condition events. At this level, we are validating not only what the system does, but also how it behaves and responds throughout the mission. Are you aware about this tool in Stateflow? It's a very good one. We can check the behavior at the same time checking the logic behind of this behavior. And by simulating both the physical dynamics and the operational logic, we can identify design issues early. This is very clear. You can verify requirements and build the confidence that the system will perform as intended, okay? And when integrated into a larger mission architecture. I have a quick question in this slide, and please answer by Shaita again. We have to have your answer. How do you verify that your system behavior is correct across all, operating modes and transitions? Do you have a specific methodology today? How do you check this behavior? Even for your radar system, for your UAVs, maritime systems, satellite. Could you answer, please? How do you check today? The answer can be, Fernand, I'm using Simulink and Stateflow as well. Or it can be another tool. Or you can say, Fernand, I am not verifying the behavior, but I want to. It can be another answer. Please answer by chat. The final step is validating the system in realistic, operational scenario. Up to this point, we have defined the mission objective, develop architecture, analyze the trade-off, design the individual systems. Now we are bringing everything together in the high-fidelity environment. The way to visualize is to co-simulate, right? Fernand, I want to see using my LiDAR systems. I want to use camera. I want to simulate in 3D animation. So here, the drones operates with a realistic, urban, how can I say, urban scenario, right? In just city. So you can see the buildings, the streets, and you can see details in 3D environments with the sensor models, environment effect. It can be raining, sandy. You can define the environment, okay? And what is the benefit to co-simulate, Fernanda? This allows us to evaluate not only whether the system works, but whether it can, successfully perform under the real conditions. And by co-simulating the platform, sensors, environment, the mission logic, working together, we can identify issues, okay, that may not be visible in isolated subsystems if you're testing, and gain, greater confidence in a mission readiness. And finally, this provides a kind of, I would say, bridge between the system design and the operational reality to ensure that the engineering decisions, how can I say, translate into a mission, okay, success. And if you don't have this kind of visualization, it's possible to do with Simulink 3D. We have options if you want to include LiDAR with a point cloud data, you can do it as well. Okay. So let's go to our demo. What do you have in this demonstration? So this is what is the mission in this case? The mission Wildfire search and rescue, okay? And it's operating using BVOLOS. What does it mean? These abbreviations: beyond visual line of sight, autonomous drone system. And what is the scenario in this mission? We have a beyond visual, we have this bivolus type of drone, right? And we are using cell on wheels. We used to say call, okay, for communications coverage. What is the challenge? There are so many challenges. So communicating requirements between the teams, delivering system requirements from the mission objectives, optimizing the entire system as the details change, managing, communicating, design changes in real time, maintain the reliable communications during the flight, monitoring the battery life, this is important, and ensure the autonomous navigations and waypoint following, okay, if my drone is following the waypoints. And what is the final objective? To minimize the time to complete the mission and to maximize the wireless connectivity. Okay, and how we can do it? I split in 5 parts. First, architecture overview. We are taking a look in this hierarchy for looking for system architecture. Generate coverage over the terrain. So we need to set up this. Design the path planner. Okay, all this logic behind of the path planner. Modeling the drone. So what is the behavior behind how my drone with the controller, my flight control is working, and how to optimize the drone autonomous behavior. We look in the end what we can do to improve these systems. Okay. Okay, let's start looking to the architecture view. At this stage, we are using System Composer, as you know, to define the functional architecture of the Wildfire search and rescue mission. Rather than starting with the platform implementation details, we begin by capturing the mission activities and how can I say, and the information flow between them. Okay. The mission starts with the initial laydown, where the operational area is identified based on the available information. And then we move for identify the ROI, where the region of interest of the search grid are generated. Next, we establish the communication network when we determine where the cell on wheels or we calls, okay, as you remember the abbreviation COW, should be positioned to provide this coverage. Okay, and finally, where drones execute the search operation while maintain the communication with a network. Okay, I would say that the system composer allows us to represent these mission activities by the interface, the information exchange at the system level. And this provides a common language for the mission planners, okay? The communication of the engineer, the autonomy of the engineers, and the system architects to collaborate and trace requirements throughout all development. So we are using, in this case, okay, it's running. We are using in this model scene events. This is a discrete event simulation environment. What is the benefit? You can model message passing and event driving interaction between the mission elements. Exactly this one. Yes. For example, we can simulate events such as a drone reaching a waypoint, a battery level dropping, below as a threshold, loss or recovery of communication, detection of the fire hot spot. What else? Commands being descent from the ground control station. All these events trigger actions throughout of the mission and can help, evaluate the mission time. So this is very helpful. And you can see the blocks are different than Simulink. So you can see the difference between the scene events and the Simulink. Okay. It's going, I don't know, it's a little bit slow, but you can see or these communications we are using state flow for platform behavior. In this case, from the antenna. What is the the communication between the platform behavior behind of this message of the antenna? So in this case, we are adding a time to change the transition from the drive to position to deploy the antenna. This is a very common when we talk about the time to transit. Okay. And then finally the UAV platform logic. Okay, how does it work? How they follow path and return this communication? As you can see, we have everything in the same environment. Okay. You can see after run, we can see exactly the answer of these messages and these events. You can combine the system architecture, the system behavior, and the logic behind of that, these sub-components. Okay, great. Okay, now let's take a look. Let's jump into our simulation and calculate this coverage now. So in this simulation, we have two cell on wheels vehicles available to our disposal, okay? And we have chosen placement for them to are on the roads that afford easy access to this potential search area. Okay, so you can see details about the latitude, the longitude. And this coverage map can be read as a follow. So when the drone is a yellow area, so you can see that the signal is transmits, okay, is received by our ground station with a power of 60 dBm minus 60 dBm, okay, which is well above our threshold to close the link. So you can see how, okay, perfect, yeah. So you can see details about this coverage. One thing this draws to our attention immediately is that are the gaps coverage in the middle of the search region. When the drone is flying, in this case for 50 meters of altitude, despite this, we can see that the main lobes of our antennas are pointed at the search region. So we seem to be on the right track, you know. One potential solution to increase our ability to close a link between the UAVs and the ground stations is literally to fly higher. So let me show you how we can improve this coverage increase. Okay, so yes, exactly in this slide. So I compile in different altitudes. So it exactly demonstrates how the communication coverage change as the UAV altitude increase over the complexity terrain. For each image, you can see show the predicted coverage map and the different altitude ranging from 10 meters, you can see in the first picture, to 210 meters. And the colors literally represent the signal strength, with the warmer colors indicate the stronger coverage. And the cooler colors indicate weaker, coverage on the showered areas. The red maker represents the target area, while the blue marks represent ground units or the communication nodes. At the lower altitude, such as 10 to 50 or almost, 70 meters, the terrain features like wheels, and the ridge blocks at the signal, creating, I'd say, significant coverage gaps. As the UAV gains altitude, it achieves better line of the sight conditions, reducing the terrain, the shadowing, and expanding the coverage footprint. In the round of 130 and to 200, we see the substantial, improvement in coverage around of this target location. Beyond that, the coverage becomes more uniform, right? And the gains begin to diminish, indicating the trade-offs between this altitude. So these analysis helps to identify the optimal, UAV operating altitude to literally maximize the communication coverage during this wildfire response and search and rescue mission. So what you can do in this case, you can import GIS data if you intend to work with this GIS data of a target area. Okay, you can place these true calls in COW to provide this coverage, to calculate this coverage at different altitudes, considering mountains and all this observed line of sight communications. And the minimum altitude for hours, to be connected with the drone with, 150 meters, at least to be in the middle. Now let's take a look and design the path planner. Let me play. So after define the mission architecture, I would say that design the UAV path planner, it's very important. We are using, you can see, I don't know if you know, but we are using MATLAB Live Editor to create this repeatable, workflow for mission planning. As you can add your code at the same environment, you can see the results. And the workflow starts by preparing this mission geographic. Okay, we load the base and map and the terrain to elevate this data, which gives the understanding of the operation and environment. And looking for the mission environment, we add environment information such as a fire locations, a smoke region, mission boundaries, and the communication coverage areas. So this exactly approach allows us to plan the roads are not only efficient but also operationally visible. And then for the communication, an important aspect of this mission is to maintain the connectivity with this COW network, rather than simplify, find the shortest path. We are designing the path that keep the UAV inside of this communications coverage while performing the search mission. Okay, this is exactly that we are showing for the smoke, the free area, the good communication, it's okay, the bad communication. We can put in a map everything. And regarding to the search area planning, once the environment is defined, we use the coverage plans to automatically generate a search patterns for this designated search region. So these planners ensure that the entire area of the interest is systematically covered while minimizing the mission time. Okay, so you can see in this picture the way to optimize this. For this transit between the search areas, we can use the path planning algorithms to generate efficient routes around of the terrain constraints and emission hazards. The resulting path is then covered into waypoints that UAV can follow during the simulation. At the same time, we are looking to the digital thread. Okay, what is the powerful here is that the mission data communication constraints, the terrain information, it's another challenge, and the vehicle behaviors, all they remain connected. If the operational area changes, a fire spreads, right? Or the communication coverage is updated. We can quickly regenerate and evaluate new mission plans. So this is the way to optimize. It's open and you can see more details. How about this path planning? And contour this area. The green area, you can see exactly the search that we are looking for. And you can see exactly if my drone is following these waypoints. Okay, let's take a look at how to modeling the drone. So once the mission plan has been generated, we need to model this drone. This is a big model, big Simulink model, that we can execute those of these commands, okay? In high-level structure, the drone model is organized into several key components that you can see, the waypoint follower, the obstacle avoidance logic, the flight controller, the vehicle dynamics, or the plant model. So this is very important. And together, these components allows us to simulate how the UAV behaves during the mission. So these inputs from the drone, we have desired YAL, desired position, and the current UAV state. The desired of this position comes from the mission planner, okay, and the waypoint follower, while the UAV state provides information such as a position, the velocity, and the orientation. So we need to make sure if everything is correct in this point. And the waypoint is following, they receive the mission waypoints generated during this planning phase, and you can see exactly if the following the order the complete the search mission. In parallel, we have the obstacle avoidance subsystem. This allows UAV to react these obstacles or mission constraints by modifying, the commands and trajectory while still progressing toward the mission objective. This is particularly important in the wildfire scenarios where the terrain, the smoke zones, or restrict areas may affect the planned road. This is very important. Regarding the controller plant, the controller converts literally the desired position and heading to control commands for the drone. So all this, those commands are then sent to the plant model, which represents a quad rotor dynamics. This is a block inside of my model. I don't know if you know, but this quad rotor motor block, we are using to capture the essential flight dynamics needed for the mission level. This is good because you can access the mission performance without requiring the high detail of the flight control implementation. So in this case, if you don't have these details, so you can use this block and help you to analyze and provide this flight dynamics, for the mission level evaluation. And you can see this is state flow for UAV behavior. This is a key part of this model. The state flow is a subsystem in this case for a component. You can define the UAV operational behavior using this literally state machine. So you can analyze the behavior based on the state, okay? And you can add this condition to move the state. A good example, the UAV can transition between states for takeoff, navigate of search area, execute the search pattern, return to the base. All these conditions you can set up in state flow. They are kind of triggered, by the mission events. Waypoint completion, communication status, as I show you in the previous slides, battery conditions, everything you can combine to follow your logic. So now you can see running the model and what happened with my behavior based on my UAV. So you can see exactly my drone. It's accelerated this video. Otherwise, I spent a lot of time. Okay. And they are literally following the points. Okay. This model literally combines emission logic, waypoint following, obstacle avoidance, flight control, and this quadrotor dynamics, allowing exactly the simulation how the UAV executes the mission in response to a real world event. And finally, in the previous model, we saw how the UAV follow the waypoints, avoid the obstacle, but here I want to show how we can optimize the drone, autonomous behavior. So you can see we have some sliders, right? This allows to quickly explore different scenarios without modifying the model itself. So I'm giving some zoom. Okay, so we have the maximum flight time. This is the first parameter that you can see. This represents exactly the endurance of the UAV, okay, by adjusting the value and how much the search area can be covered. Recovery time. So this is the model in this time required for system to recover from the interruption or complete recovery operation before to resuming the mission. We can use this for understand how recovery procedure impact in the mission. And recovery timeout. So we also have this slider that defines how long this system will attempt recovery action before declaring unsuccessful or and transitioning, to alternative state. So we are using state flow as well to test how this mission logic responds. And for last one, we have a minimal SNR threshold is another important parameter if we have a signal to noise ratio or SNR. Okay, so we can check the communication between the UAV and the COW. I don't know if is it good to visualize. I'm sorry in this video, but you can see in different case. We have the case one for lower, drone power consumption by using a lower power. So you have some details to reduce the mission completion speed, but may extend the maximum mission duration. We have the second case to increase the connectivity of time by using the high power, high gain wireless receiver, and the maximum battery powered flight duration is reduced, but reduce the maximum mission duration. And we have the last one, in the last case, to increase the timeout between the connectivity, recovering the mode by adding onboard memory storage, use a low gain receiver, and also extend the maximum mission duration. So we have different cases and scenarios that we can represent using this virtual model. Okay. Let me know if you cannot see. I'm sorry about these colors. But this is a very good point to share in different scenarios. Okay. I have another question. How do we increase the confidence the mission will succeed before we deploy in the real assets? This is a quick example. We are evaluating different regions of interest in our ROIs, right? As the wildfire involves, new search areas may need to be added. So as a priority it may change and the communication conditions may vary, rather than manually redesigning the mission each time, we can rapidly, generate and evaluate alternative search plans. So we can looking for a trade-off analysis. For example, one search area may provide an excellent communications covered, but require, a longer flight path. Another region may reduce the mission time, but increase the risk of communication loss. So using exactly this simulation, we can quantify these trade-offs and select the best operational strategy. So the idea and optimize these models, uh, I would say this is the sense of the mission engineering. Instead of evaluating individual components in isolation, we are evaluating how the complete system performs against the mission objective. And the key takeaway from all this demonstration and model design allows you to evaluate the mission effectiveness early. So this is the main idea, to do this as soon as possible, to analyze all these scenarios, the worst scenario, the best scenario, sorry, and reduce the development risk, reduce the engineering hours, to improve the collaboration across the engineering teams, so to make better decisions through the simulation. So this is not a future, this is a reality. All these big companies are doing this. They definitely helps to deliver more capable and reliable system faster. The idea is to simulate everything before to deploy, and then to spend money with the physical components, physical systems, right? So I have another thing to discuss. So the mission engineer requires ability to represent a wide range of system operating across the multiple domains. I know you have different backgrounds. You are, as our attendees today. So here are some examples, the type of system that can be modeled and analyzed that include underwater platforms, radar systems, communications networks, UAVs, helicopters, space systems, maritime assets, and as well autonomous and AI-enabled systems. So if you're using one of these components, I would like to invite you for our next event. My colleague Abdirahim will be discussing about the platforms, focus on emission engineering, how to accelerate the platform.